practice from last night. Shush. And then we will go over how to balance in acids and then how to balance in bases. So that's actually that's going to be 99% of the types of problems are balancing in acids and bases. This will be like 1% of the problems. But I had to teach you this way just in case the whole balancing with oxidation state changes. Plus, it made you really practice oxidation states. It made you kind of recognize what was oxidation, what was reduction. So it's more of an introduction to balancing with redox reactions versus our go-to technique. So remember, what's the purpose of balancing in these ways? Why are we learning this method? It's easier than balancing by inspection, just by like looking at a huge equation going, okay, trial and error, trial and error, trial and error. So you're supposed to have a technique, a method. So I'm going to walk through number 5 real fast. I already have it balanced here for you, but let me show you the process. Whenever you solve your balanced chemical equation first, the first thing you did was write oxidation states. You probably went across the whole thing to write oxidation states. So the ones that you saw change in, and I know everybody probably did this, was chromium 6 and chromium 3. Yes? Did you guys get 6 plus on that one?
Yeah.
Yeah? Okay. And then whatever this acid is. And then, so we went phosphate 1 plus, phosphorus with a 1 plus, phosphorus with a 5 plus. You got that?
Yeah.
Okay, so then you connected your brackets and you said chromium to chromium was a loss of total 3 electrons if you just looked at the 6 plus gain of 3 electrons from 6 to 3. But this is where it becomes a little tricky. At this point, so I labeled it in the color code. So I went red or pink first, and then green, and then blue. So if you saw that you had 2 chromiums here, but 1 chromium here, you actually had to count that first. If not, you would have never been able to get your electrons balanced. So if there are 2 of them here, 1 of them there, I had to add a 2 here. So I said, was a 2 now 4? Let me show you that. It was a 2. So that you had 2 times 3 electrons transferred, you get total 6 electrons transferred. So the total electrons transferred was 6. But then you look at the hydrogen, and that was a total of, phosphorus and phosphorus, that was a total of 4 electrons. So with 4 electrons and 6 electrons transferred, you had to multiply by something to get them to the point where they're equal electrons lost and gained. So 4 and 6 kind of meet in the middle at 12, so you multiply this one by 3, you multiply this one by 2. Whenever you multiply this one by 2, though, only one of the coefficients is really, no, actually both of the coefficients are going to change because we need to make sure we have a total electron transfer. So I added a 2 here, and then I made this I had already added a 2, I'm going to make it a 4 now. So that's why they're called temporary coefficients, because you can change them if needed, especially when you're trying to make your electrons, your charge balance. So then we had how many total electrons were transferred from chromium to chromium, or in the chromium process? 12, because we had 4 chromiums and 4 chromiums. Each chromium are gaining what? 3. So total of 4 chromiums gaining 3 is 12 electrons transferred. And then from this one, sorry, I did not show you, the 3s get transferred as coefficients here. So then we had 3 phosphori, each losing how many electrons? Each losing 4, so 3 times 4 is 12. So then the green ones are staying now, the green coefficients are staying. Then you had to balance by inspection the rest of the way. So I actually started with potassium, so I saw 4 potassiums here, so I put a 4 over here for KCl. That made me have 4 chlorines, plus the chlorines already had present here, so that's 4 times 3 is 12, plus 4 is 16, so there's 16 chlorines on this side. Over here, the only chlorines present are in the HCl, so immediately I applied the 16 coefficient there. Then after I saw I had 16 H's, I was like, all right, I got to go and balance the H's on that side. Did I see any more H's on this side? Yes. So I had 16 plus 9 is 25. Okay, so 25 H's on this side, and then double check. We already had here 9, so then you needed 16 more, and that's where you could do 2 times 8 is 16. So I added an 8 there. I think that's it. Okay, so total electrons transferred in this whole shebang. 12. Okay, it's not 24, it's 12. I just want to make sure that you understand the 12 electrons are transferred from the oxidized one to the reduced one. It's not a total of 24, it's just 12. Okay, so I will come back and do number 7, just because I want to make sure that we talk about acid-base today in thoroughness so that you guys can actually practice today in class. not right now. I want you to do this with me because yesterday's not 2 days ago. Okay, so this looks like something important. It's not. This is just an example. Okay, so in terms of reactions, a lot of times our reactions are going to occur in the presence of an acid or in the presence of a base. And the reason why is because reactions occur really slow sometimes. So how do we speed them up? Add a catalyst. So the definition of catalyst is what? Something that's added that speeds up a chemical reaction. Like in our bodies, what biomolecule is a catalyst? A protein, which is an enzyme, right? So this is actually the biological connection to chemistry. So like the biochemistry part, which everything that we talk about is essentially could be biochemistry. But basically on this slide, I want you to know that an enzyme, which is a protein, is a catalyst. That's in the biological side of things. And enzymes are usually large biomolecules. Proteins are very large in most cases. In our side of chemistry and in our side of biochemistry, we generally talk about acid catalysis or basic catalysis. And those are just really small entities, so H pluses and OH minuses, and they can actually help speed up reactions, and they assist proteins in doing that. So it's not just one or the other. Generally, they're together. So we're going to talk about in the presence of acid or in the presence of base. We're going to start in the presence of acid today and learning how to balance that way. This is my favorite way to balance redox reactions. So, and this is just an example. We make esters this way. So you guys learned in your orgo notes, ethers. Remember ethers? There's something on ether side. Esters are a little different. Esters are actually fragrances. So wintergreen, banana, pineapple, anything like that has a scent as an ester. So that's just for fun. Okay, so here's how you balance. This one's a lengthy step process as well. Take a picture, write down what you need to, do whatever you need to do. I would actually prefer you to write this one down this time because this one's the ones you're going to use, I'd say 90% of the time. So I'll explain to you how this works. Whenever we have a redox reaction, one of the reactions is going to be an acid. One of the reactions is going to be oxidized, and the other one is going to be reduced. So that's not actually a full reaction. That's why this says half reactions at the top. So for example, yesterday, actually let me just pull one from our stuff today. That's a half reaction because it's only half the story. So whenever you're looking at your reaction, a lot of times I'll give you both half reactions together. Your job is to pull out each half reaction. And I knew that this was the half reaction that from the total. I'll write the total thing up here for you. E2 plus. That's actually the whole reaction. That's kind of like the NIE part of it. So when you're pulling from a total reaction, each half reaction, you look for the things that are related to one another. Because iron is going to yield iron, chromium is going to yield chromium. So each half reaction would be dichromate yields chromium 3+, and then separately, iron 2 yields iron 3+. So that's what it says, divide equation into half reactions. Then you always want to balance starting with things that are non-H's and O's, because when you're balancing in acids or balancing in bases, generally those are aqueous solutions. So these two things will come into play, these two steps here will come into play simply because it's an aqueous solution. So there's a surplus of water, and if it's in the presence of acid, there's a surplus of H+. So before you can even balance that way, you want to balance things like chromium and iron in this example. So I'll actually walk through this example in just a second. After that, your job is to balance with water. That will balance out the oxygens, because there's no free oxygen in water, right? It's bound up, so you can't just pull out O and say, let me just add O to this side versus this side. You balance it by adding waters. This H+ is just because it's simply an acid, so there's free H+ floating around, so you can add that to balance out the reaction. So what we did first here is we balanced all the atoms. Then we're concerned about charges. In the previous style, what do we do? Charges first and then atoms, right? So now we're doing charges at the end. So after you balance, after you look at the charges, and this right now is gibberish, I'll do an example, but after you balance out the charges by adding electrons on either side, so on reactant side or product side, not both, one's going to be on one reaction, one's going to be on the other reaction, then you have to make sure your electrons lost and gained are equal. How did we do that earlier? We added a multiplier. So we multiply something. We add a multiplier. And then we're actually going to smush the two half reactions back together in one big reaction. Okay? This will kind of become second nature to you. You will do this a lot. This is the more detailed version I just said. But I think the other one is better for us. This is something I'll come back to if I need to. This is a lot more detailed if you need more details. But I'm going to explain it through an example first. So that example is here. Let me hide some of this. Write down the top reaction for me. So the top reaction, what are those names?
Dichromate
Plus
iron 2 sulfate.
Yields.
Chromate 3 sulfate.
Chromium 3. Yeah.
Chromium, yeah. Iron 2 sulfate times potassium ion.
Cool. My honors chemistry kids would be like, oh my gosh, you guys are so smart. So smart. You are so smart, but just saying. They would be amazed by that. Okay, so you got your reaction, and this is the demonstration I kind of just had on the board a second ago. So what you want to kind of figure out first is what's really important here. And so if you think about it, you know, potassium is always going to be soluble, just like Gia is in our solubility rules. So potassium and potassium are going to be spectator ions here. And then what else do you see that has not changed? Period, from beginning to end.
Sulfate.
Sulfate, okay, so it says it right here, right? So your sulfate here, here, and here is actually kind of irrelevant. And that's simply because your oxidation states are not changing on that because sulfate's charge is -2. If sulfate is still -2 here, here, and here, you still have the same number of oxygens here, here, and here. That means sulfur's oxidation state is what? +6, right? Here, here, and here. So it's not involved whatsoever. So those actually are spectator ions. Okay, so then how does that kind of reduce down to the part that's important, which is the NIE? We get dichromate, iron 2+, chromium 3+, and iron 3+. And notice I didn't actually write down any coefficients here because that's our job. We're balancing this for atomic by mass and then by charge. So actually just kind of pulled out the important pieces. Now, what are the two half reactions? We relate them. We see which reactant went to which product based on similarity. So one of the half reactions is going to be chromate going to chromium 3+. So you always want to leave some space on the left and the right of this, so kind of write this in the center of your paper. All right, so I ignore the two there, okay? So if you just had to pull this out, you'd say dichromate goes to chromium 3+. The very first step in balancing a half reaction is to balance the non-H's and O's. Well, that means chromium in this case. So therefore you add a coefficient of 3 there. What's the next step? We just balance the non-H's and O's. Balance the O's by adding water. So you'll see there are 7 oxygens on the reactant side. We need 7 oxygens over here. So how many waters am I adding over here? 7, because each water carries 1 oxygen. Okay, then I balance the what? H's by adding H pluses. So I actually just added 14 H pluses over here. Yeah? So I add 14 H pluses over here. Okay, next up. Balance charge. Okay, so we need to look at the net charge of reactants versus the net charge of the products. So the net charge here is we have 14 pluses, so that's 14 plus, a 2 minus. So 14 plus and a 2 minus make what? 12 plus. I'm going to kind of just write that right here for us. Oops, 12 plus. What's the net charge over here? 2 times 3, so then and 0. So what's the total charge over here? 6 plus, because it's 2 times 3 plus, so it's a 6 plus. So I am dealing with electrons here. So I need to add electrons to one side to make the charges, the net charges, equal to each other. So am I going to add electrons to the 12 plus side or to the 6 plus side? 12 plus, because I can bring 12 plus down to 6 plus by adding how many electrons over here? 6. So add 6 electrons. I don't have enough space for myself, but there you go. So on the reactant side, you have 14H plus dichromate plus 6 electrons yields 2 chromium 3 pluses and 7 waters. That's that half reaction. Done. Next half reaction is what? Okay. So irons are balanced. Are there any O's to balance? No. Are there any H's to balance? No. What's the next step? Electrons. You're balancing electrons. We obviously can see the overall net charges that is 2. The overall net charges is 3. Where do I add electrons? This side, how many of them? 1 electron. Okay, so how do you know you're right at this point in time? One reaction is being oxidized. One reaction is being reduced. That's because electrons are on one side and then the other side. So the first reaction we have here, we have electrons in the reactants. Is that one reduced or oxidized? Electrons in the reactants. Reduced. I told you yesterday, immediately you should be able to tell if something's reduced or oxidized based on the location of the electrons. Electrons are in the reactant side, they're reduced. That means that chromium is reduced. This one, oxidized because it's actually losing electrons. So iron 2 is losing electrons to solution. That's why they're being produced. They're going away. Okay, so what do you notice about our electrons though? From reaction 1 to reaction 2. How many electrons in the first one? How many electrons in the second one? Are they balanced? No. Your job is to balance them by adding multipliers. So I'm going to add a multiplier by multiplying this entire half reaction by what? 6. Because I have 6 electrons here, I need to get these to be 6. So that means I have 6 iron 2s, 6 iron 3s, and 6 electrons. Yay, the electrons are balanced. Last step. Add the half reactions. Mush them back together. So I'm going to kind of do that here. Have some space. I'll kind of do it here because I actually went through all the steps right there. So I have total 14 H pluses plus a dichromate plus 6 electrons yields. I'm sorry, not yields. I'm still having to add the irons. Plus 6 Fe 2 pluses. So I have everything on the reactant side here now. Now everything on the product side. 2 chromium 3 pluses, 7 waters, and then my second reaction, 6 iron 3 pluses, and 6 electrons. That is the whole entire shebang. That is the final answer. Oh no. Is there anything that's on left and right that we can cancel? Because they're the same, so nothing changed. 6 electrons. You should always cancel electrons. 6 electrons here, 6 electrons here. They should never be there because if you balanced it correctly, there are equal electrons on both sides. Therefore, we cancel them to signal that nothing really happened here. Just cancel that or to show that they have negated each other. So our final BCE would be everything but the electrons. So you're going to get in the hang of not writing the electrons down to begin with because you know they're going to cancel, especially if you balance it correctly. Okay, let's do another one.
So,
Yeah.
yes. Please.
Yes.
Yeah, let's do it.
Yeah. I'm going to do it from a reaction standpoint. This is number 1 on y'all's little teeny sheet because I'm saving trees. Remember, because I got yelled at. So write out this reaction for yourself. Write out the whole number 1. Yeah. You add the reaction? Okay. So then tell me, first up, break this into half reactions. What's one of your half reactions? Which ones look similar? So ClO 1 minus yields chloride ion. Okay, so I'm going to stick with that one reaction first, that one half reaction. All right, so are the chlorines balanced? Because I'm looking at the first, the non-O's and H's. The chlorines balanced?
Yes.
Yes. Now you have to balance oxygens by adding 1 H2O on the reactant product side. Okay, so I have 1 O there, so I need 1 O here. Next balance, H's. So what do I add? 2 H pluses. Don't forget it's H plus because that's the acid component. It's a hydrogen ion. Okay, so I've got Cl's balanced, I've got O's balanced, I've got H's balanced. I'm done with mass. What's next? Charge. What's the net charge over here? Plus 1, because I have two 1 pluses and one 1 minus, so that sums to be 1 plus. I'm not going to write that down always, but I'm going to write it over here for just for now for us. This overall charge, 1 minus, because chlorine's a 1 minus, water's neutral, so that's a 1 minus. Who gets electrons? The reactant side, because I need to get a plus 1 down to a negative 1 charge. So how many electrons do I add to this side? 2. Because 2 minus plus a 1 plus yields a 1 minus. Okay, so that balance, that half reaction is done. Is that half reaction oxidized or reduced? Reduced, because the electrons are in the reactant side. Okay, you good? All right, second half reaction. So we just did that one and that one. So it's what? Thiosulfate yields that thing. Okay, it's okay. It's peroxy thiosulfate and stuff. Okay, so first step, balance non-H's and O's. So what do I do? Just put a 2 in front of thiosulfate. All right, and that actually does a lot. That balances the S's to be 4 and the oxygens to be 6. So I don't have to add any water. Do I have to add any H pluses? No. What's next step? Charge. What's the charge here? Minus 4. So 2 times the negative 2 is 4, negative 4, and that's a negative 2. So what do I add? 2 electrons over here. Okay, and are the electrons balanced? The electrons lost equal to electrons gained. Yes, I don't have to add any multipliers. Now what do I do? Smush. So summate. Sum these together. So I already see that the electrons are the same on both sides, so I'm actually not going to write them. I'm just going to say, good, good. I've done a good job there. Then just rewrite the equation. H plus hypochlorite plus 2 thiosulfates yields this guy, peroxy thiosulfate, chloride ion, and water. Yay! It's a process, right? But once you get the hang of it, you get really fast with it. Let's do number 2. I'm going to do maybe 2 more examples here, and then I'll let you guys practice. Tell me the half reaction you're going to start with. Copper solid to copper 2 plus. This one's easy. Coppers are balanced, there's no H's and O's, go straight to charge. So 2 electrons over here, because I had a net charge of 0 here, net charge of 2 plus, so 2 plus and a 2 minus equals 0. Done. Next. All right, nitrate yields. What's that? No, it's not ion. Nitrogen dioxide. Okay. I know it looks, that's a plus. What's next? I got my N's balanced. O's. By adding 1 H2O to the product side. Then, so 2 H pluses on this side, on the reactant side. Net charge. Net charge on this side. Plus 1, because it's a 2 plus and a negative 1, so it's a plus 1 charge and a 0 charge. So who gets electrons? The reactant. How many? 1 electron here, because I had a 1 plus, so that brings it down to 0. Now you have a problem. Electrons do not equal electrons are lost and gained. So what do? The bottom reaction by 2. All right, so that makes our electrons, that makes that 2 electrons, and that cancels with those 2 electrons. And then I'm going to add these together. Just don't forget to distribute that 2 all the way across. So what's your total reaction? Copper solid plus somebody. 4 hydrogen ions plus 2 nitrates and 2 nitrogen dioxides and 2 waters. Can you reduce that at all? No, because the coppers are 1s and everything else is a 2, except for the hydrogen. Okay. All right, so you guys try. I'll reduce these already. Do 5, 6, 8 right now. 5, 6, and 8 right now. Under acidic solutions, that's under the ones we just did. 5, 6, and 8 right now. And then I'll decide on how many on the last ones I want to do. There are 19, so whatever I'm doing is helping. It's less than 19. So take about 10, maybe less than 10 minutes, and then we're going to talk about balancing and base. And base is actually just as easy. So when you get down to the half reactions on this number 6, you do see that you got 6 electrons from the first half reaction that I've written out, and then 2 electrons on the second half reaction that I've written out, and that needs to be balanced by using the multiplier of 3. So then you get 7 total reaction. You get 7 waters plus 2 chromium 3 pluses plus 6 times 3, so 18 H pluses plus 3 times 1, so 3 bismuthates yields dichromate plus 14 H pluses plus 3 times 1, so 3 bismuths, 3 pluses, and 9 waters. Then your job is to simplify. So don't forget, whenever you have the power to do so, you need to look on both sides and then cancel things that are the same, or simplify by subtracting a number of waters, for example. So we have 7 waters here, 9 waters here. That actually simplifies down to 0 waters on this side, leaving 7 of these cancel, 7 of the 9. So that leaves us with a 2 water left over on the product side. You guys see what I did? Okay. And then what else do you see that's similar?
H plus.
Right, so I have 14 H pluses on this side, 18 on this side. If 14 cancel here and 14 cancel here, that leaves us with what here? 4. So the coefficient ratio should be 2 to 4 to 3 to 1 to 3 to 2. Because those other ones are gone. And I would actually rewrite this as 2 chromiums plus 4 H pluses plus 3 bismuthates yields dichromate plus 3 bismuth 3 pluses plus 2 waters. I would rewrite that, okay? And then you guys do number 8. You feel a little bit better as you go through it? Keep working through your process. I'm going to quietly do mine too. You guys can do yours. It's okay to talk to yourself. You're doing your charges. Anybody else who's actually got support?
Then why is it multiplied by 2?
Because there are two, when you did your charge balance, did you get 2 electrons and 5 electrons?
Yeah.
The rule of redox is that electrons lost equal electrons gained. So you have to make them equal, so you have to use a multiplier.
Okay.
And it just, essentially, it's the multiplier is just a ratio in which these reactants react together. It's just balancing.
So when you have 2 electrons on one half reaction and 5 reaction, you just do the opposite.
Yep. And like, sometimes it's easier. So like if you had 3 electrons on one and 4 electrons in the other, you could make that equal 12. So you don't multiply, well, like I said, it's still the opposite, 4 and 3.
Got it.
No. Yeah. So if you're to the point on number 8 where you got your half reactions, you've multiplied by 2 and 5 to equate the electrons lost and gained. Then you start to sum. The sum is huge, right? So you can actually reduce these down still more. You have 15 waters on product side. You have 8 waters on reactant side. So the 8 waters go away on reactant, leaving a leftover of how many waters on the product? 7. What's up?
What is the 3 OH plus? That's 30.
3. That's 30 H pluses.
Oh.
5 times 6. Yeah. I was like, I don't know what you're talking about there. Yeah, that's 30. So sorry, we had how many leftover waters on the side? 7, because we had 8 or 15 and 8, so 15 minus 8 is 7 leftover. And then H pluses on both sides. We have 30 on one side, and how many on the side? 16. So what do I cancel? So we have 16 that go away, leaving us left over 14, and everything else stays. So your total NIE of 2 Mn 2 plus 14 H pluses plus 5 bismuth 8s yields 2 permanganates plus 5 bismuth 3 pluses and 7 waters. The NIEs are long. They will always be long. It's because there's so much present in the solution that's acting to balance the charge and the atoms. All right, do you know the flow of this? You feel good about that? I'll tell you what. Huh?
Can you go back to 6?
Yep. I will tell you which ones I want you to do on that in a second. Yeah.
Are we still going to have to do it the other way like we did last night, or can we just do it this way?
If it says, so that's a really good point. If it says in the presence of acid, you absolutely have to do it this way. Or if it says sulfuric acid was added to this reaction, don't include sulfuric acid as a reactant. Assume that's saying in acid. So anytime there's acid present, you have to balance as if it were in acid. If it didn't say that, I will say to assume that usually, because the balancing by oxidation state changes is usually not going to be our go-to, because it's always catalyzed by an acid or base. So you're going to assume it's probably an acid. If it specifically says in base, then you assume it's in base. So we're going to balance by base now. Okay, base is not different really whatsoever. Okay, we're going to do exactly the same process, but what do you think is not going to be able to be free in solution if it's in the presence of a base? H pluses, right? So let me just kind of tell you what we're going to do, and then I'll have you write down the actual instructions for it. Okay, so this H plus right here, there's no way in heck it's going to be there if it's if this reaction is happening in a base. So what we do is we add 14 OHs to that to negate the H pluses. But if you add 14 OH minuses, what does that do to your charge? You're adding 14 negatives, correct? That totally messes up your charge balance. So if you added 14 OH minuses here, you just throw an extra 14 OH minuses on that side to keep your charge balance there. Then you collapse H pluses and OH minuses into what? What do they come together to make? Water. And then if there's extra waters on one side, you just cancel them. It's an extra couple of steps. So right now, actually, we're going to practice. I'll tell you of those what I want you to do. This is the base. This is the detailed version. See what I just said. Read it though. Write down what you need to. And then I will actually walk through a separate example, not from our previous example. Well, I'll show you, but that's about it. So bases actually are just the small addition to what we just did. So it's not much extra at all. So write down what you need to for your steps. paraphrase because that's very detailed. I'll do like 3 examples and then we're done. You guys can see the example from previously. That was my demo example. You can see how that works there.
Just go back and just do it.
That is the first step, right? Oh, yeah, go for it. Okay, so I'm going to go ahead and do an example, and I'll come back to this if I need to, but I'm going to scroll down here first. So previously in our demo example, we had 14 H pluses left over in the solution. That's impossible if it's present in base. So all the basic ions, hydroxides, would neutralize 14 here. But to keep our charge balance that we worked so hard to get to, we need to add 14 negatives or OH negatives on this side as well. That creates a situation where we have 14 waters present. That creates a situation where we just have extra 14 OHs, which is totally fine. That keeps our charge balance. Those 14 waters will cancel with some of the, or with all 7 of those waters. That leaves zero waters on that side and pulls us down to 14 waters on this side. So it's just the simplification step again. Not anything real extra, except for knowing that it makes sense for 0 acid to be left over in base. So I'm going to start with number 1 here. Okay, balance as if it were acid first. You should be pretty good with that flow. Number 1 here. So your first step is what? Half reactions. I'm just giving myself some space. These do require a couple of lines. So if you need paper for some reason, if you're scared of killing trees, it's all good. Got you. But you do need to write out each thing on a separate line because it's way easier. So you got your half reaction. What do you do first? Shout it out to me. So add 2 waters here. Then what? 4 H pluses, acting as if this were an acid. Then what? So what's the net charge reactant side? So a 2 plus, because we have 4 pluses and a 2 minus, so it's a 2 plus on this side. There's a 1 minus on this side. How do I get 2 plus down to 1 minus? Add 3 electrons to this side. Okay, that one's done. Sulfide goes to sulfur. What do? Where? Come on, people. Thank you. 2 electrons here. Balance your charge by doing what? Charge. Multiply the top by 2, bottom by 3. Okay? Sum that baby up. You'll see that your electrons do cancel because there's 6 electrons regained and lost. So I just go ahead and account for that. So that gives us 8 H pluses, 2 chromates, act like point and top, 3 sulfides, yields 2 CrO1 minus, 4 waters, 3 sulfurs, and that's it. Yeah. All right, so we got down to as if we were balancing an acid. Everybody else get this? I didn't skip anything, right? Looks good. Thanks, guys. All right, so what's my next step? Add OHs to what? To whatever the H plus number is, right? So I need how many H plus or OH negatives here? 8. But what I add on one side, I absolutely have to do to the other side to keep my charge balance, right? So I need to have 8 negatives on both sides. So that condenses down to 8 waters. So I'm just going to put a scratch through that and just instead of, I'm like literally showing my work, but I'm going to say 8 H2O up top just to realize it's now water. So then now my simplification step comes in. I see 8 waters on this side, I see 4 waters on that side. Tell me what the end BCE is. 4 H2O because 4 of those 8 were canceled with this. Okay, so 4 H2O plus 2 chromates plus 3 sulfides yields 2 CrO, 2 1 minuses, plus 3 sulfurs plus 8 hydroxides. There we go. So what we did was just balanced in acid like normal, and then we said, okay, this is in base. I can have no excess H pluses. I must account for that. Not too much extra, right? Okay. So do go ahead and do number 2, which is this one, balance in base. You have this on your sheet as well. It's just that it's on the bottom. Nope, where's my sheet? It's the bottom. It's right here. Yeah, it's the bottom one. I'm going to do another one. So, half reaction, permanganate. Actually, I'll just write it over here. Permanganate, 1 minus goes to MnO2, solid, okay? What do we do? 2 H2Os. Sorry, I have to give myself more space. Oh my. There we go. So, adding 2 waters to this side to balance up my O's because my Mn's were already balanced. Balancing my O's, I see that now I have 2 waters on this side, so that gives me how many H pluses? 4 H pluses on this side. And then charge balance. Okay, so I have an overall of a 3 plus charge on reactant side, 0 on the product side, so I add 3 electrons to bring a 3 plus down to 0. I think that's the hardest part. You guys feeling okay with the charge balance?
Yes.
You just have to look at everything and say, okay, 4 pluses, 1 minus, that makes a 3 plus. That has 0 charges, that's a 0. You bring the positive down. You always add electrons to the more positive side because it must go down to the more negative side. Okay, and then you bring OCCOO. So oxalate down to carbon dioxide. What's that first step?
Add water on the
No. Yes, you see 2 carbons. I need 2 carbons. Good job, guys. That's something a lot of people miss. So I have 2 carbons. Now my oxygens are actually balanced. So 4 oxygens. Next step. No. See, I have 2 times 2. That's 4 oxygens there. There's 4 oxygens there. We're good. We actually have no H's present. Charge balance is next. What's my charge, or what do I add? 2 electrons to the product side. Okay. 3 electrons, 2 electrons. I must do what? Multiply top by 2 and bottom by 3. Net gets 6 electrons total, so I'm just going to go ahead and cancel those out. So, 4 H pluses, I lied, 8 H pluses. Okay, 8 H pluses, plus 2 permanganates, plus 3 oxalates, yields 2 MnO2s, plus 4 waters, plus 6 carbon dioxides, and we're good. Okay, so we just balanced as if it were an acid. First step for balancing, or to adjusting it to be balanced in base. So we're adding 8 OHs because there are what? 8 H pluses. So you're taking the number of H pluses and negating them with all hydroxides. That's going to be present on this side too, because we absolutely must do it on both sides. If not, you wasted your time doing charge balance. Now we have 8 negatives and 8 negatives, so we're good here. This reduces down to what? 8 waters. So I'm just going to write 8 waters there and totally ignore that this is even present because it's no longer present. Now I have a total NIE of 8 waters on this side, 4 waters on that side. What do I do? Totally cross out the 4 waters here. That cancels out 4 of them here, leaving me 4 waters. I'm just showing you my thoughts, okay? You can write down less than me as long as you can do it correctly. If you can't do it correctly, it's cool, waste paper, get it done. So we have 4 waters left, 2 permanganates. I literally have to write this out. I'm not good with keeping this stuff in my head, so I have to write it. 2 manganese dioxides, 6 carbon dioxides, and this remaining 8 OH negatives. If you feel good about acids and bases, then go ahead and start on acids. I'm going to tell you which ones I want you to do though. Where's this down? 11. So on the acid one, I want you to do 11, 14. Yeah, 11 and 14 on the acids, and then I'll tell you what I want you to do on bases. If you need some more help making sure, I really want you guys to get this done in class. You got about 20, 11 and 14 on the acids. That's on acids. I'm getting ready to give you bases. Hold on. Don't jump the gun here.
You do that nice on bases too.
Huh?
You do that nice on bases too.
I will. Just don't pressure me, man. Promise. I'm trying to make sure you guys have practice, but not too much practice.
This is the OH.
I can come. I just want to tell you real quickly what's on bases. Four, 6, and 8 on bases. 4, 6, and 8. You have 5 homeworks. Oh, plus read the survey of Redox Reactions Lab. It's like 15 reactions. Read through it so that you know what you're doing tomorrow. Basically, we're going to have fun throwing some stuff together, making observations, but we are going to be balancing them if they're present in acid, or if they're present in base, or if they're just simply a reaction. We can balance by inspection. But everything, like I said, is a redox reaction. It just happens to be more complex if they're in acid or base. So you're going to just read the lab for me so you're prepared for tomorrow, so you have an inkling of what's going on. Okay? If you want to spread out, help each other, do what you got to do. You have a hand up?
No.
If you need my help, you just have to ask. I'll run around. One of my favorite ways to balance stuff.